I guess I'll just start. The first item on our agenda, welcome to Chicago, except I just got here too. The first item on our agenda are the pedagogical talks. These are intended for people, in case the pedagogical people don't know this already. We are intended to speak to people who don't already know about, in this case, electron microscopes.
Now you tell us?
I'm discharging my responsibilities. So David Muller will tell us about electron microscopes for about 20 minutes, and then we'll have 10 minutes of questions. Then Thomas Arias will tell us about density functional theory, which is a tool that has been incredibly useful in figuring out materials questions that allow us to make good choices in the experiments. And then again, 20 minutes for Pietro to tell us about free electron lasers. David.
Okay. So we're a bright beam center, and what I want to talk a little bit about is how does beam brightness help us in the business of electron microscopy? And electron microscopes there are companies that are billion-dollar companies, and their only business is selling electron microscopes. Every industry that makes stuff probably has an electron microscope out it. And the electron microscopes, particularly the transmission electron microscope folks, the one number they rarely care about is the resolution of their instrument. And if you're doing electron microscope research, it's often become a very convenient shorthand for bragging about how good your particular tool is. And there's a long history to electron microscopy. It's a business that started in about 1930 with Ruska over there, and the main point was light microscopy had run out of steam by the turn of the 1900s. And a diffraction limited light microscope today looks pretty much like what a light microscope would look like in 1900, except it's more user-friendly. And there are, of course, a lot of super resolution methods today that make light microscopy a lot more interesting, down to maybe about that level over there. But if you ask yourself, how do I know what a virus looks like? And the polio virus in particular, the answer is because of electron microscopes. And for about 50 years, the way electron microscopes got better was that you just kept pushing up the beam voltage of these instruments, because that made the wavelength shorter and shorter and shorter, until you get to a point over here where the energies of the microscopes are so big that all your papers start with the words "irradiation damage study of." So that is sort of a dead end, and there are maybe only 1 or 2 microscopes at that voltage that are still operating today. Most of them have been decommissioned and replaced by machines with aberration correctors. And I'm going to make a connection between aberration correctors and improving the emittance of, or at least retaining the emittance of an electron beam. And the systems that do aberration correction have optics, as I'll show you, that are very, very similar to what you would see in a large synchrotron ring. And that led to substantial improvement in resolution at much lower beam voltages that made it a much less damaging process. And around about 2008, that had more or less matured and leveled off. And we haven't seen a lot of improvement on the hardware side, but recently, with improved detectors, we've been able to push that resolution a little bit more. And you might ask yourself, if the shortest bond length in nature is an angstrom, why do I want to get below an angstrom? Why does it matter? And so here's a very quick picture. This is MOS2. It's a two-dimensional material, and it's got a hexagonal structure. But if you've been looking at physics today lately, if you take 2D materials and you stack them one layer on top of the other, so the lattice fringe, the lattices are rotated like that, you get moire, you get a beautiful moire pattern and very interesting electronic structure, particularly when the rotations of the moire fringes are incommensurate with the lattice. So this is a state-of-the-art microscope at its highest resolution, which is an angstrom because you have to work at a very low beam voltage not to blow these things apart. And then here it is with our new detector running at 0.4 angstroms. And you can see there's a huge improvement. And this is now the highest resolution electron microscope image in the world, at least for this week. And as other people adopt our detectors, I'm sure we'll get beaten. So that's the motivation for why we want to keep pushing on the resolution of microscopes, because there are still some atoms here we haven't resolved.
So each dot representing what?
Yeah, each dot, each light dot is a single atom. The very bright ones are two atoms because it's one on top of the other.
So it's not just, is there an atom, but where the atom is can have subtle, subtle physics charge density waves.
Exactly. So that's the stuff that Leno works on. Is if you put one of these materials in and you cool it down, and you now have a charge density wave. What the electron microscope tells you is where is the nucleus, right? If I have an STM, I know where the electron cloud is, but I don't know where the nucleus is. And so a lot of work on high TC superconductivity is only half the story, because you're looking at the electrons, but you're not looking at are the ions following the electrons or not. And so that, I think, is going to have a very big impact on the field, at least I hope so. So I have now stolen a slide from Pietro, and he may well use this one again. Beam brightness, and he has a very nice, very early history of when did we start to worry about beam brightness. And that was when we started to have electron microscopes. And the beam brightness essentially is I have a piece of phase space on the bottom, a solid angle, and an area which is the spot size of my beam, and then the amount of beam current I'm trying to dump into that small piece of phase space. And empirically, as he sort of notes out, your brightness and your volume of phase space is conserved, or certainly you can kind of make it less dense if you mess things up. But it's linear optics is just going to squish and reshape that piece of phase space. And so there's this trade-off now of the smaller the spot size, the larger the beam divergence, and there are going to then be limits on what I can handle. And so, if you write down that formula and rearrange it a little bit, there's the beam current, which is going to be the number of electrons in the amount of time that I'm going to be doing things. And so when I'm doing ultra fast, that becomes important, how close I'm trying to squeeze stuff. The number of electrons is very important for the contrast and the resolution of the image because of Poisson statistics. We're always noise limited. If I have n electrons, my fluctuations are square root of n. So if I only have 100 electrons, I'm going to have 10% noise. And I'm not going to be able to resolve features less than 10% contrast. The spatial resolution here is in the radius r, and then the coherence is the convergence of the beam. So you can rearrange this formula over here, and you can find out this for an electron microscope, where resolution is my key metric. The resolution scales as 1 over the beam divergence, and it goes as a square root of the brightness and square root of the beam current. So if I want good resolution, I need a good beam current, and the higher my brightness, the smaller my spot size is going to be. And if I don't have a bright source and then I need a lot of beam current, I'm in trouble. So the main one I want you to remember is the spot size is going to scale as 1 over the beam divergence.
So beam bright, that has also I, and I is cancelled, no? Denominator.
This one, I've done a little bit. This one didn't cancel out. I've got one other piece of information I had to throw in there for that formula over here. But what you can kind of see from this one is, as I increase the beam current, my spot size blows up on me.
So then beam micron is from earlier I.
So I start with this formula, and then I need one other piece of information.
So that it has to be corrected. That's why it's not exactly.
Yeah. So so the first one to think about is the resolution of my system depends on the beam brightness and this divergence, and the divergence is going to be set by the optics of the system, and the beam brightness is a fundamental property of the source. And so two ways to look at this problem. This is, I've stolen this again from Pietro, and he probably will use it again when he starts to worry about free electron lasers. But the six-dimensional brightness, now I'm thinking of the full phase space, and so I'm worrying about both transverse and longitudinal coherence issues. And what you'll sort of see is the cold field emission guns, which is our favorite source, and we'll talk a little bit more about, are the highest brightness sources that we know about at the moment. But they're also tend to involve very low beam currents. And that is part of the challenge we're going to have. And we're also very well away from the quantum limit, given that these are fermions and there's a degeneracy problem with that. We have, in other words, a lot of room for improvement, but a long way to go, and a long way to go. So here's another way to look at it. This is from Jared, and now we're looking at the emittance, and the emittance is the phase space on the bottom over there, and then factoring out how much beam current you've got sitting in the system. And now what he's plotted is the beam power, so that's the beam voltage times the amount of charge in the bunch. And you'll notice that this is 1 over emittance over here, and the electron sources are very low emittance, and conventional imaging, it's got a fairly broad space over there. The type of imaging that most people like to do today for materials problems is the STEM mode, where I have a focus beam coming in rather than a broad beam coming in. And the focus beam, then obviously as I push up my beam voltage, the emittance improves as well as the beam power goes up. But again, these are compared to other sources, extremely low power, but also extremely low emittance. And you can kind of almost get a sense of this feeling of a trade-off between trying to increase the beam power and trying to get yourself a low emittance. And again, these are probably the lowest emittance sources out there.
So where would you like to go?
Beam power, for me, I'm probably okay sitting at this 10 to the minus 5 point. Be nice to go lower because, well, it depends, right? I mean, 2D materials, I'm going to damage, I want to go lower in the beam power. Thick things, biological samples, I probably want to sit on that line there. I clearly want lower emittance, but I don't have to go over there in beam power. Unless I'm starting to worry about ultra fast, in which case I want to take this and move it over there. And now I have a time-resolved source. I don't know if that's even possible, but if it is, then you go shut down all these free electron lasers. So a little bit, what do these DC sources look like? Because they look very, very different to the photocathodes. The simplest source is basically a hairpin filament from a light bulb. And that is very low brightness. And by low brightness, I mean probably brighter than the 3rd generation synchrotron. Now, these things are about $20 each, and you can pick up a microscope like this for free. People throw them out. The Lab 6 filament is sort of more common workhorse cheap tool. Brightness is order of magnitude up. It's still got a horrible energy spread. But these crystal tips, the little flat facet on the top, they're 100 microns, and Lab 6 is a low work function, so those things are easy to convert to ultra-fast sources. And so FEI uses this as their ultra-fast source. The more common field emission system is a Schottky field emitter. So this is a field emission, but which is heated up and thermally assisted. And you field emit from the very tip of the sharp tungsten needle, and then to lower the work function, there's a blob of zirconium that is heated and it flows down the needle tip and with a little bit of oxide, you get zirconium oxide because there's always a bit of oxygen in these systems. They're not great vacuum. And that's where you get your film emission from, and they stop working when the zirconium blob is run out. The highest brightness sources are cold field emitters. These are that CFAG on the previous plot. This is just a tungsten wire, 311 oriented, and electrochemically polished to a sharp tip. And it's very, very similar to an STM, scanning tunneling microscope tip, the thing that you use to drag around and do atomic resolution imaging with.
David, what's the scale?
So this is a 10 micron scale bar, and the tip of this thing is maybe, you know, a 10 nanometer radius of curvature. And then as you use this and you heat it up and blunt it to keep it, as you try to clean it, it blunts out. And when it gets to about 100 nanometer radius of curvature, you know it no longer gets a large enough field to field emit anymore, and then you have to go change it. This needle, again, this is trying to think how big that is. That's probably maybe 100 microns long needle over there. This one, often the tip is about a micron at the edge. It's running at higher temperatures, so you don't want it as sharp. And these have the good numbers over here, the high brightness, the low energy is the cold field emitter. It's also possible to get the Schottky up to those numbers if you run it correctly, and most people don't. But that's just sort of physically what it looks like. So now the resolution limits to the system. And the reason I want to kind of stress this is an electron wavelength at 100 kilovolts is 0.037 angstroms. So I don't have a 0.037 angstrom resolution microscope, right? Our best resolution is 10 times worse than that. A typical instrument, I'm more like 100 times worse resolution than the wavelength. So if this was a camera, I have an F number of 100. F number of 100, if you're a photography buff, is a really, really, really slow lens. And the quality of our electron lenses is not much better than that of using a beer bottle. That we have horrible aberrations of the lens, and so the two aberrations that are the ones that we worry about in the beginning are chromatic aberration, which is that the curvature of the lens is just wrong, and in fact, it causes all the rays to bend too strongly, so that rays that are coming from far off the optic axis are bent to a crossover at a much earlier distance than the rays that are close to the optic axis. And for a lens to focus, all the rays have to come to focus at the same point. And that means if I have too big an aperture in my lens, the beam has a little blurry disc over there. And the minimum blur here is going to scale with the cube of the beam angle. Now remember, the source size that we saw on that first slide went as 1 over the beam angle. So it's clearly in opposition to this thing that my spherical aberration and my chromatic aberrations, which is different wavelengths come to focus at different places, push me to using small apertures. But if I have a small aperture, I'm going to first of all have a diffraction blur, this is the Rayleigh limit, which is the size of the Airy disk, and it scales exactly the same way that the source size scales, 1 over alpha. And for most systems, because I need beam current in the system, I'm source size limited, and so the numerical prefactor here is usually the numerical prefactor of the source size, not that of the intrinsic Airy disk. They both scale the same way, they both need large aperture sizes. And I can't get a large aperture size because of my aberrations. So here I am just analytically, rather than doing a proper wave propagation, just adding these up in the quadrature. It gets you the right scaling, it gets you the wrong prefactor. But you can see over here is at large aperture sizes, my spherical aberration blows up on me, and my probe gets big. At small aperture sizes, I don't have enough beam current, and so then the minimum detectable size and my diffraction limit both scale the same way, force me into very, very, very poor resolution. So in fact, an optimum that you end up with, which is a trade-off somewhere over there, and that trade-off is what gave me my 2 angstrom spot size in an uncorrected instrument. So, do we have to live with this? Why is this a problem? Why are electron lenses so lousy? And the very short answer to why electron lenses are terrible is thanks to Mr. Maxwell and in fact Mr. Laplace is really to blame. That the
Nature to blame.
yes, the curvature of my electromagnetic fields is just too curved to act as a lens, and that means that any lens will have both spherical and chromatic aberration, and they're both positive and non-zero. And these are the conditions under which this is true, and this was proved in 1936. If I have a cylindrically symmetric optical system, I need a real image, and I need a real image because I actually want to do something with it. The fields are not time varying, and that there's no charge on the axis. And with these constraints, it's impossible to get a better lens. So obviously, we have to break at least one of these assumptions. And by 1948, Otto Scherzer had sort of suggested how to do it. Dennis Gabor had some ideas as well. You remember he was the guy who won the prize for holography, Nobel Prize. He optimistically thought by 1950 we'd have built an aberration corrector. It took another 50 years before that worked out, and I'll give you a sense of why that is. So the way electron microscopists deal with getting better lenses is we give up on the cylindrical symmetry. We do a hideous power series expansion in multipoles to correct the optics. I would point out that with CBB and with ultra-fast systems, we have one other opportunity open to us. We can work with time-varying fields. And so it's possible to do aberration correction with a time-varying field. And now that you have short pulses, that is in fact possible to do, and it hasn't really been very widely explored. But that, I think, is a huge opportunity going forward. So just a very couple of quick definitions. My lens aberration, which causes my rays to bend, can be described by the phase shift, which is sort of the bending of the surface as a function of angle, which is, think of it as the path difference that I had to go along to bend incorrectly away from the ideal line of equal phase. And that's my aberration function chi. And there's a huge number of aberrations. Normally you think of the spherical aberration, but if I do a power series expansion, there's a lot more of them. So typically you describe aberrations of the lenses as a power series expansion. In optics you use Zernike polynomials. In electron optics we tend to use complex polynomials, both because it's easier to do the computation and there's some problems with how the Zernike polynomial assumes a fixed lens aperture. And both of those are bad news, and so this is a more convenient formulation. All I want to point out is it's a power series expansion where I have these multipole-like polynomials times a spherical harmonic-y thing, if you like. And so the aberration coefficients, they're labeled by the polynomial, how many zeros it has going out, and how many times how many nodes it has as I go around an angle. So C10 would be defocus, C30 is a spherical aberration. Each of these things has names because people have suffered off them. But these are sort of our aberrations and our limiting aberrations. It's a huge expansion, and at some point you just might as well do it on a computer. And that's in fact what happens. Now, how does this connect to storage rings? Well, when you're doing your lattice elements in your storage ring, and the way you're tuning and fixing things up, you're using a lot of sextupoles or hexapoles, depending whether you want to be, I guess, Greek or Latin. And the sextupole is the key element we need for an aberration corrector. So if I take a sextupole, it actually has a negative spherical aberration coefficient. That's a big deal because all my round lenses have positive spherical aberration coefficients. It has all sorts of other horrible aberrations that go along with it. So you can't just stick one sextupole in. And the trick to build an aberration corrector is the right-hand side over here. It's two sextupoles that are more or less set up to be conjugate to each other if you follow the ray diagrams for the axial and the field rays. And that helps to cancel some of the other orders of aberrations that otherwise would add up. And this little element over here The trick sort of is you try to take your round beam, push it into a line, and then you can cancel aberration one way and then you cancel the other way. So this element over here with the sextupoles is our simplest form of aberration corrector. This is the CIOS design, which is Harold Rosa's design. Rosa was Georg Hofstadter's thesis advisor. And so it's not surprising that these elements are what you'd use in the synchrotron. And this thing's got a lot of lenses in order to make it work and transfer everything back to the magnetic lens. So you need about 27 optical elements all properly focused to build the simplest corrector. And we tend to use much more complicated correctors that they tend to have more like 81 independent tunable lenses to get it all to work. So there's a lot of alignment problems that come with this.
So for designing that many elements,
Yeah.
purely combination of analytic and simulation, or how does it?
Yeah, so a lot of it was analytic. Well, it started off with a lot of analytic work and exploiting symmetries, and then putting things back to back and inverting them so that things cancel out, and relying on crossovers so that, you know, around if I have a beam that's elongated in a line, then it doesn't matter if I have horrible aberrations this way, because it's a line and everything's going through at one angle, and then I get to correct things only along the line. It's much more manageable. It's not at all clear to me that this is the optimal way to do it.
But then real machine errors, how do they?
So that's why 50 years ago, even though people knew this kind of idea, they couldn't build these things. Because by the time they built it, they didn't have good enough precision on the machining. And then by the time you've lined up lens 81, lens 1 has drifted out. The precisions you're talking about are parts per billion on the current. So you have to build a power supply that's supplying 2 amps with a part per billion stability, right? So, you know, you're talking nanoamp stability on an amp power supply. And these things drift in, some of the aberrations are numbers of the scale of 2 nanometers. Right? And those things can drift over the period of minutes. And we get to line up this thing once a day. And then you have to do the rest of it by hand. Okay. So very, very hard. Alignment is hard and design is hard. In fact, it's not at all clear to me that we have the optimal design. And some of the fun things about CBB is we think we can use, say, codes like VMAD to take a look and see whether we can optimize the design and do some machine learning on the optimization. So here is just showing you the stability. Normally the way we measure stability of the system is how big is our beam? What's the spot size? And this is in fact an intrinsically unstable property. So there's a paper over here which is entitled Intrinsic Instability of the Aberration Corrected Electron Microscope. And here you can see if I want to keep the system aligned and properly tuned, and I don't want my aberration corrected to drift, you can see that my resolution is a cusp. And so it's not a nice rounded minimum, and any instability is immediately going to show up as a defocus in the beam. So you require constant monitoring and very, very short lifetime for the tuned state. And as you start to push resolution, your tuned state lifetime stability becomes shorter and shorter. So very bad news. One very nice result that my student Paul Cueva showed is that because all of your aberration functions contributing to blurring out and increasing the emittance, what you actually want to do is if you want to get an optimized system, you want to minimize the emittance of the system, and that has the beautiful property of it's convex. It's independent defocus, and that's important because defocus is the aberration, that's the one that's only a few nanometers in size, and that's the one that drifts out. So the reason why this thing looks horrible is the defocus is messing you up. Once I remove defocus from the equation, this metric is actually well behaved and stable. And so if we minimize emittance and not resolution, we think we can reliably tune this thing up much better. So that's a big deal. So how do people actually measure these aberrations? Well, it turns out you need some sample with a lot of spatial frequencies in it, so not every sample is going to work. You end up taking a whole bunch of images. You take an image under focus, over focus, in focus, tilt the beams to different angles, and then you make a measurement at all these different tilts, and this is called a Zemlin tableau, and it means basically you have to take over 40 images to get one measurement of aberration. Then you go back and tune. This is very, very slow, and it requires particular samples. What we've managed to do at CBB in the last 2 years is use a detector we've developed that actually gets us a measurement of the 4D phase space. So at every position of the beam, it gets the momentum distribution, which is the scattering angle from elastic scattering. So now I have a 4D phase space. You can convert this to a witness space. And the shift of an apparent image at a given momentum point. So if I look at the detector in K space, and then I sit at this particular pixel over here, and I scan the beam around, I will produce a real space image on axis. And if I look at another point and scan around, and that is a scattering angle that's off axis, then that image is shifted with respect to that image, and that shift is related to the gradient of the aberration function. And so by doing now one scan, I get all of the angles in the Zemlin tableau at once. And the key to making this method work is I have to be able to very, very accurately measure the shift between those two images, and those images are very noisy. So here, very quickly, is showing you the accuracy of our way of tuning versus the standard Zemlin tableau. And you can see this is 6 repeated measurements. It's way, way more accurate and way, way more reproducible. So that's a huge deal. And in order for this to work out, we needed a way to very accurately measure shifts between images, and this is what Colin and Jim Sethner worked on. And we're able to show that their registration method is much, much better, particularly when things get noisy, than the traditional Fourier cross correlations. And so that's very important for making precise measurements. So where do things go? Let's think of our electron microscope as a linear accelerator. It has a high brightness source. It has an acceleration column, and then it has all of our beam transport optics. The aberration correctors help preserve emittance, but they drift very badly. We can correct geometric aberrations right now out to about 70 milliradians, which is about a third of an angstrom. We can't get a third of an angstrom beam because the chromatic blur limits us to about 25 milliradians. So the result is our current DC electron microscopes are limited by the energy spread of the source. If you can give me a source with a better energy spread, I can give you a better resolution. I can't monochromate too much because I need a minimum beam current. And that pushes us back to the need for a higher brightness source. The same story is actually true if I'm doing ultra fast. In many cases, what kills you in the ultra fast is going to be the energy spread. That blows up on you very quickly. Mm-hmm. So that's our big challenge. Little bit of fun history. Our best, highest brightness source in the world is Albert Crew's tungsten cold field emission gun. And a little bit of history is, did you ever know Albert Crew?
He hired me.
Okay. So Albert Crew used to be a director at Argonne, and then he moved to Chicago to build his field emission microscopes. And so he built the first cold field emission STEM at Chicago, got beautiful images of single atoms running around in about 1968. And then he went on to build an aberration corrector, and he's kind of the Moses of aberration correctors because he was never able to get his to work. And 40 years later, other people got to do it. Yeah, so Joshua, there were two Joshuas, Harold Rosa and Andrei Kravanek.
I think of Joshua in the Bible, but
yeah.
your story works out nicely.
Yes, yeah. So, here's a challenge, for us is this 50-year-old technology is still our highest brightness source today, and it's crazy to think we haven't found better materials. So for the cathodes folks, that's sort of a challenge I leave out there. And then you can have fun if you're a photocathodes person plugging in and figuring out how many pulses, single electron pulses I need to meet a current of about that much. So that, I think I'm going to wrap up and take questions.
for a couple of questions.
What is the source of energy spread?
So for many of our systems, it's the field emission process itself. That's the Fowler-Nordheim tunnel. So it depends how you run the tip. So if I go all the way back to the beginning, over here, and take a look at so if I get to the cold field emitter and I run that with a very low extraction voltage, I'll get close to what the Fowler-Nordheim limit would be, and then you can see an improvement from room temperature to liquid nitrogen. Most of these other tips up the top, the energy spread is what in electron microscopy we call the Bush effect, that you're basically pulling too many electrons out of this very small tip. So the tungsten filament...
I'm sorry, what effect?
Bush effect. It's the fact that I've got a whole bunch of electrons that are coming out together, and then there's a Coulomb repulsion right near the surface of the tip, because at the tip surface the electrons are moving at very low velocity, and we typically, our extraction voltage, we've got about a 3. I have some nice plots of the exact field strength, but basically my first anode is at about 3 kilovolts, and so the electrons are moving very slowly as they come off this tip. And the reason why I'm setting at 3 kilovolts is I have to stabilize the power supply. That my emission is exponential in the extraction voltage, and so if I put a 100 kilovolt supply at that point and it oscillated, my beam current would fluctuate too much.
So the term Bosch effect is very out of date for accelerator scientists. It's probably comes from 1930s.
Right.
I think now, do you mean intrabeam scattering? Is that what you're referring to?
So there's two parts to this. There's the interbeam scattering, and then there's the just as it's being field emitted, and it's right near the tip itself. So there's the I have a first anode, it has a crossover, and there's a lot of scattering that happens.
We should take this offline. This
Yeah,
is good.
but-
No, I wanted to make a point. There is a point.
Okay,
actually.
to
The
make the
point
point.
is that if you immerse a cathode in a very strong magnetic field, let's say few kilogauss, then Bosch effect is suppressed, and it has been known for a while already, seen some, so if you can also suppress the density fluctuation effect, which transfers into longitudinal temperature. So basically, there has been a lot of work in the field of electron cooling for suppressing to suppress the longitudinal energy spread down to below thermal limits. If the microscope if you can survive with samples being in a very strong magnetic field, then I know how to suppress the energy
Okay,
spread.
we should talk, because most of our other lenses are, usually a 2 Tesla field anyhow. So I think we're in the...
One more question.
I have a quick question. There's a large part of this audience, I think, that's looking towards time-resolved microscopy.
Right.
And so as one pushes down to a few femtoseconds, so you have time varying initial pulse from your photocathode or whatever. I think most of your presentation, which was lovely, was about DC
Right.
and very stable things. But so maybe you just make some closing comments on transient microscopy.
Yeah, so the easiest way to see what the challenge there is going to be is, as I start to make that delta T smaller and smaller, I end up throwing way more electrons. So there's the usual challenge with ultrafast is I can do it with 1 electron per bunch. And that's easy for diffraction, but it's very hard for imaging, because if something moves and I take a diffraction pattern, I don't care, right? That it doesn't change the diffraction pattern. But if I'm trying to image and something moves, I'm dead. So if I do electron microscopy with 1 electron per pulse, I can do that. If I try to put more than 1 electron per pulse and I try to make it a femtosecond pulse, now the 2 electrons are going to scatter against each other. And that's going to cause, that's the huge problem that you have for the ultrafast systems, is the management of what happens to electrons in a bunch when I put more than one electron in a bunch. And it blows up on you very, very quickly. And so, you know, I think it's like a nanometer, nanosecond is kind of the number to sort of think about. And so going for atomic resolution in a system with more than one electron per bunch is extremely, extremely difficult.
This was a pedagogical talk. There was a student who had a question. So why
yes.
don't we, can you take her
Why don't
question?
you set up? Good.
Yes.
Alright, so I guess you have been talking about how it's difficult and a bit time consuming to correct the alignment of everything when you're trying to get your images. So when you figured out your way to get the scattering during your image taking, so you limit the number of data points you need to collect from 40 to 6, does that mean that you do it once and you know that it's great? Is it that you have to keep correcting as you're imaging? How does that all work?
You've got to keep doing it because you're you know, you're probably stable and tuned up for about 10 minutes. And then what happens is it's a power series expansion. So the low order coefficients are things on the size of nanometers. The high order coefficients are things on the scale of meters. So meters is not going to cause a drift problem, but nanometers does. So if you're an electron microscopist, you learn how to, the first thing that'll drift out is focus. And so everyone learns how to refocus the beam automatically. Not automatically, but you take an image, you know, you take another one and you focus until it looks good. So first part of microscopy is you're just sitting there twiddling a knob. And then there's, over time, other aberrations drift out. And so the higher order ones get much harder to diagnose. So, you know, you can correct astigmatism fairly easily, and then there's coma, and then trying to figure out combinations of these three things can be quite hard, and that's definitely an art. And we have like a little simulation program where you can look at the Rungegram and try to diagnose these things. And after a while, as it drifts even further, then it becomes impossible for a person to do it, and you've got to go back to the computer software.
Okay.
All right, I'll take